Philips' mission is to change people's lives through meaningful innovation. And for me, the key word there is meaningful. What we want to do is give the customer things they really need, and these things must function properly, and Philips being Philips, we must be best in class. No gimmicks. So for me, that is the real challenge, and the excitement for working in Philips is that we make best in class products that really work. So this is the Philips Zoom blue LED whitening lamp, which is at the centre of our whitening process. People often ask me how the light works. It's widely believed that it's a gimmick by some people, but I assure you the lamp does do something, and I'm going to take a bit of time to explain that now. First of all, we need to think about the tooth structure very briefly. As I'm sure you're all aware, the tooth is made of two principal layers, the enamel and the dentine, and these both comprise of mineral material, hydroxyapatite, and softer protein materials such as collagens and amelogens, which build up their structure. And both of those substances are actually white by themselves. They're intrinsically white. So where does the colour in the tooth come from? Well, it comes from organic molecules, stains, which can be either intrinsic or extrinsic. Extrinsic stains are things which clearly come from your diet, pigments which get onto the surface of the tooth, and as a function of time they very gradually move through the depth of your tooth during your life. And that's what we call internalisation, internalised stains. Likewise, we get some intrinsic staining. This is the other way round. This is pigments from, say, the blood getting through into the dentine from the inside out. So all of the staining and colour in the tooth is from these other molecules. It's not from the natural mineral or protein of the tooth. We also need to understand what it is that gives an object its colour. If, for example, we take a green leaf out of nature, the reason it's green is because when the light is shining on it, the green light is reflected, and that's what we see, but the other wavelengths are actually absorbed by the chromophores within the leaf itself. And in actual fact, in processes like photosynthesis, the absorbing molecules are excited, and that energy is then converted into various sets of reactions which produce photosynthesis. So when it comes to the stain molecules in the tooth, which are yellowish red in colour, we have to understand that these are yellow-red because they are reflecting yellow and red wavelengths, and they are strongly absorbing the blue. And that's why we use the blue light in the whitening process, because they are directly absorbed by the stains, and that energy then is available for chemical reaction. So some whitening processes merely remove the surface stains, but in a professional whitening process we want to do rather more than that. The idea is getting rid of the stains all the way down to the dentine. And in fact, certainly in an older tooth, most of the staining is in the dentine. The enamel is translucent, that is fairly transparent to most wavelengths, and you can actually see the colour of that aged dentine through the tooth. So it is essential that we get the agent down to the dentine and get the chemistry working there. The other thing about the dentine, as you know, is we put down secondary dentine throughout life, which is building up in thickness, and that is constantly internalising more and more stains. So the dentine actually becomes yellower as you get older. In our laboratory in Cambridge, we've studied the bleaching chemistry in quite some detail, and this flowchart here is rather complex. It shows all the reaction pathways which are going on. At the centre of this is the chromogen, the stained molecule itself, and you will see that hydrogen peroxide can indeed directly interact with this chromogen to shorten its conjugation length and take away its colour. However, those reactions are actually quite slow, and what we find is that if we apply blue light, this is absorbed directly by the chromogen, it excites that chromogen, and then those reactions are much faster. And that's the essence really of the blue light technology. A couple of other things to note are really the effect of pH and temperature. Basically, if we raise pH, this helps the process, but if we go above pH 8, things happen far too quickly, and the peroxide is broken down very rapidly into water and oxygen, which are chemically inert. They don't contribute to the whitening process. Likewise, if we apply heat by whatever means, and in the past some people did this by infrared, this has really no effect other than to accelerate the decomposition before the peroxide molecules have had time to diffuse into the enamel. We think of the stain as having a chromophore region. That is a region where there is a carbon backbone of alternating double and single carbon bonds, typically up to about 30 atoms long, and this is where the blue light is absorbed. It's absorbed by electrons within those bonds. Now when those bonds absorb the electron like that, the chromophore becomes activated because one or more of those bonds is either broken or the electron is put into an excited state. Hydrogen peroxide is diffusing through the teeth. This is a process that takes about 10 or 15 minutes for the peroxide to reach the dentine, but actually when a peroxide molecule comes into the vicinity of any activated chromophore, it reacts with it very quickly. Typically those reactions cause breaking of the double bonds in the conjugation length, and this results in termination groups like hydroxyl groups, as you can see here along the chain. This effectively shrinks the conjugation length. That means that the molecule no longer absorbs blue light. Its absorption resonance is now pushed more to the UV, to shorter lengths, and thus the stain appears colourless. This picture here nicely summarises the work we've done on extracted human testing. What's plotted on the y-axis is the delta E, the shade change, and on the x-axis what we're varying here is the peroxide concentration. And you can see the three lines are results taken in the dark and with the lamp at its low and its high setting, the low setting being the 50 milliwatts per square centimetre and the high 190 milliwatts per square centimetre. And you can immediately see what a difference the light makes. And this is particularly important in Europe, where we're restricted to 6% hydrogen peroxide usage. So if you look here at the 6% peroxide data, which is 6% peroxide being the limit for use in office in Europe, you will see that in the dark, for an hour treatment, you can only get 2 shades of whitening, and this is barely noticeable. But in the light, we're getting here 4 or even 5 shades on the high lamp setting. That really is quite a good result, a surprisingly good result perhaps, at this level of peroxide. So you can see from this data that especially in Europe, where the use of peroxide is capped at 6%, it's virtually impossible to get a good result within an hour's treatment time without the use of light, which gives you the 4 to 5 shades. This is actually quite surprising, but we believe the only way to get effective whitening result in Europe, certainly within an office treatment time of an hour, is to use blue light. Well, peroxide in its native state is about pH 4, so it's acidic. It's a bit like orange juice. It will slightly demineralise your tooth, but there's a balance in the mouth. There's a constant mineralisation and demineralisation which keeps things in steady state. So provided treatment times aren't too long, the demineralisation and remineralisation takes care of things. Now in our product we actually use a pH closer to 8, so the level of acid attack is far less. As many of you know, the apparent colour or shade of the tooth depends on the state of hydration. It's a bit like a bath sponge. When it's full of water it looks one colour, and when you squeeze it to get the water out it goes a lot lighter, and this is also true of teeth. What we're doing in this figure is we're cycling between 15-minute treatments and then 15 minutes of rehydration in water. And you can see the shade, the delta E, is oscillating as we go from a treatment to rehydration again, and this is the effect of drying. Now the solid dots there, where we've got a change of up to 10 shades, a massive change in whitening, this is caused simply by taking the extracted human teeth and putting it under a bench under a hot lamp. And you can see that this is far more than you would get of real whitening from a peroxide whitening treatment. And some of the other things shown in the figure as well are lesser treatments. So for example, the solid circle is where the tooth is simply placed on a bench for 15 minutes and allowed to dry in the air. And you can see we can get up to 5 shades of false whitening recorded just by dehydrating the tooth in this way. So it's very important to understand hydration, and even more important that when you develop a whitening process that you actually make sure you're characterising the teeth when they're in a fully hydrated state. And we do that by measuring after 2 hours immersion in saliva to get them rehydrated. We then repeat those measurements after 7 days and 30 days to be absolutely sure that the tooth is showing real whiteness and not dehydration. So what we actually incorporate in our product is ACP, that's amorphous calcium phosphate. The calcium ions and the phosphate ions are kept in separate barrels of the syringe, and when they're mixed they combine together and they can then start to precipitate out a kind of amorphous form of enamel. It's an amorphous calcium phosphate, as the name suggests. What this does then is, firstly, it can help remineralise the tooth where any demineralisation might be occurring, but also it can actually plug some of the pathways in the enamel and the dentin itself, rather like some of the sensitivity products do. And in this way it can reduce any incidences of sensitivity or pain for those few people that actually do have sensitive teeth and do have some discomfort during a whitening process. Let me just start with the early history of tooth whitening with lamps, which goes back 10 years or more. In those days people were using hot incandescent white light sources which kick out not just the white light but also a lot of heat, and they were kind of hoping that the light and the heat would in some way activate the hydrogen peroxide, that is, turn it into reactive ions and radicals to accelerate the removal of stains. But actually that wasn't the case. Firstly, if you heat peroxide, it does accelerate the reactions, but actually it makes it bubble. It turns to water and oxygen and it reacts away far too quickly. You see that bubbling, and the peroxide doesn't have time to diffuse into the tooth down to the dentin. That process takes about 10 minutes, and it requires the peroxide to be rather more stable while that's happening and not degrading away. So heat isn't good from the chemistry point of view. And additionally, people were hoping that the visible light from the lamp would activate the peroxide directly, but of course it doesn't. If you think about it, hydrogen peroxide is colourless just like water. It doesn't absorb visible light. The second problem with heating the tooth is dehydration. What I've got here are some extracted human teeth that we use in our testing, which we keep in artificial saliva, and if I take one out here and put it on the bench, this will start to dehydrate quite rapidly. So perhaps some of you are still not so convinced about the blue light, but let me just give you another example. This is one of the blue light sticks that are used for curing your dental restoratives. Well, they work on this principle. What we do is we put a pigment, a yellow pigment, into the restorative, often it's camphorquinone, which absorbs the blue light. Now the restorative doesn't look yellow because you need so little of this that it's still pretty white in appearance. When the camphorquinone absorbs that blue light, it becomes excited in exactly the same way. The electron is excited and it becomes very reactive. And what happens in this case, we're not reacting with peroxide as in tooth whitening. What we're doing now is generating a whole series of chain reactions which cause that restorative to set, and it sets very quickly, as you know. So when we research our product, we go through what we call a kind of funnel process. As you can imagine, clinical trials are very expensive and you can't do them where you check every parameter that you can adjust within a formulation. So we save the clinical trials for the final formulation, and we do as much as we can there in 3 other stages before that. The first thing we do is we just study the basic chemistry in test tube. As you know, the whitening is a mixture of chemistry and physics. From the physics point of view, there's diffusion and optics, etc. coming in. We take that away at the first stage, and what we do just in test tube is look at the simple chemistry. So we use various stain solutions such as tea, coffee, red wine, etc. We apply the peroxide, and by looking at the colour changes, we can work out the kinetics of the chemistry. And we can do that whilst looking at many, many different parameters. That's at the top end of the funnel. So we can look at pH, concentration of peroxide, and all sorts of other things. Once we've understood that chemistry, we then bring in some of the physics. That's the diffusion and the optics. And we do that by using bovine teeth, cow teeth, which are stained deliberately using the solutions as above, and therefore when we're looking at the rate of change of the colour there, we're understanding the physics as well as the chemistry. So having brought in the physics through the bovine samples, we then on a smaller set of experiments look to see exactly what happens on human teeth, and we do that by using extracted human teeth. These have natural colour, unlike the bovine ones, and much more represent the real world. Then finally, from those results, we can work out pretty much what are the best few formulations and then test them at clinical. And as you can appreciate, in the clinical trials, there's all sorts of variation there with different people. The N is larger, there's a much bigger population that we're looking at, and we end up with good quality statistical results, which is what we use behind our claims. So when you see things on the box, such as up to 5 shades, that's come from clinical testing in our laboratories. As you can see here, we're looking at stained bovine, extracted human, and then results from a clinical study. And the 2 columns here are with and without light, and you can see that we get pretty good correlation between the results. We can predict from both bovine and extracted human teeth quite well what we think we're going to get from a real clinical trial. That doesn't mean to say we don't need a clinical trial, but what it means is we've got a lot of confidence in the pre-work we do before going to an expensive clinical trial.